Hello everyone and welcome to MV Tutors. I'm Tsolo and I'll be looking at question 1 with you from the prelims of physics. Physics paper 1. Please don't mind my voice. It's a little bit under the weather. But yeah, so I'll be taking occasional breaks just to cough and drink something so that I'm still audible. Alright, so let us get started with question 1. Okay, so 1.1. Alright, it says inertia is a property of an object whereby the object. Okay, so basically where I would start, I would ask myself, what is inertia actually? Inertia is like the resistance to movement. Okay, so if an object is stationary, inertia is the resistance to move. And if an object is already moving, it is the resistance to change direction. So you just want to stick to where you are, or you want to stick to your motion. Okay, so let us see the options that we have. All right, so A needs a force to accelerate. No, it doesn't want to move. Nor does it want to change direction. Okay, comes to rest when the force that has set it in motion is removed. It's inertia basically is resistance to movement. So C has kinetic energy, no. D is not able to move. I don't like that that phrase, but that is basically what inertia is, the resistance to movement. So it doesn't want to move. So yes, it's not able to move. So we'll go with D. Okay, now a box mass M rests on the floor of a lift which is accelerating upwards. Okay, so yeah, you have a lift, it's definitely moving upwards. You have the tension in the cables, that's what causes the lift to go up. Okay, you have the force of gravity here, but this thing is accelerating upwards. Okay, so if we use our equation, we know there is acceleration. Okay, so it's accelerating upwards. The lift's acceleration is A, and the acceleration due to gravity is G. The net force on the box is equal to. Okay, so let us see. I think let me make this G. Oh, yeah, I can just leave it as FG, it's fine. But yeah, so now what is the net force equal to? Okay, so over here for the net force, you know, it's if you take upwards as positive, you have tension minus the force of gravity. Okay, but this side you have acceleration, so you have acceleration going what is it, up, and then you always have gravitational acceleration going down. So therefore your acceleration is actually going to be A minus G. Okay, so ultimately if I multiply this out, I will get MA minus mg. Okay, and this is just my resultant force. So if I look at the options available, definitely not A, definitely not B. C, yeah. D, no. So we are definitely going to go, let me just circle what we have. So we're going to go with C. Okay, just lift this up. Now, a learner drops an object from the 15th floor of a building. 1 second later, the learner drops another identical object from the same position. So as both objects are in free fall, the distance between them will be, well, it will, not will be, it will. If you think about it, not intently, you would say that they are identical. They are dropped from the same position. So the distance between them must, be the same. Okay. Yeah, but actually that's not true. Okay, so the distance between them will increase. Okay, and another way of actually showing you that is if you use one of the equations of motion. Let's just go have a look. It's, I think, this one. If you want to know the distance between them, so you can say delta y is equal to initial velocity times t plus half a delta t squared. I hope I'm right, but I think that's correct. All right, so if you look at object 1, ne? After 1 second, okay, so these things are dropped, ne? So if they dropped, initial velocity is 0. So after 1 second, okay, we're going down, so I'm taking down as positive. Sorry about that. So I'm taking down as positive, so 9.8 will be positive, okay? And then I have time, well, it is 1 second. So this is what object 1's distance will be, okay? So the distance between object 1 and 2 at 1 second, if we take our calculator, let me just pause to get the calculator. Okay, I have the calculator. So if we just check that on the calculator, so we have a half times 9,8. So the distance between them initially is 4,9 seconds. Okay, so for those who think that the distance between them will be the same, it means at 2 seconds, why am I saying seconds? Meters. It means that at 2 seconds, we should have the same distance in between them. But check what happens at 2 seconds. Okay, so so for now you have object 2 there and you have object 1, okay, and the distance between them, we said it's 4,9 meters. Now at 2 seconds, okay, let's just check on the calculator. We have 9,8 times 2 squared, which is 4. Now the distance between them is 19,6 meters. Do you see that the distance actually expanded? Okay, so for now you have object 2 that just came up from the starting position. It was actually 4,9 meters, but this is object 2, but object 1, okay, I didn't draw that to scale. Now it's 19,6 meters. So the distance keeps getting bigger as these objects fall. And why is that? So object 1 will always have an advantage, okay, because when you drop something, especially from a high place, its velocity keeps increasing as it goes down. Once it touches the ground, it has reached its maximum velocity. So that time advantage that object 1 has will always ensure that the distance between it and object 2 are increasing or is increasing. Okay, so our answer then will be A. Okay, and then 1.4. Okay. All right, so a trolley with mass m moving with a constant horizontal velocity of v on a frictionless, okay, so a trolley of mass m is moving with a constant velocity of v. If you have constant velocity, there's no acceleration. All right, so on a frictionless track, okay, a block with mass m is dropped into the trolley, all right, from above. So the final velocity of the trolley and block will be, so this is a typical momentum question. Okay, so where you have the momentum before is equal to the momentum after. Okay, so what is happening with the momentum before? You have the mass of the trolley and the velocity of a trolley. Okay, so here acceleration doesn't really count, but yeah. So you have the mass of the trolley and the velocity of the trolley. And then you have the mass of this block and the velocity of the block. Okay, so at this point, I believe this block is stationary. Okay, so this value here, the velocity of the block is 0. Okay, but afterwards, you have the mass of the trolley and the mass of the block, okay, together. And they have the same velocity afterwards. All right, so we know the mass of the trolley is m, okay, and then there's the velocity of the trolley. And this, like I said, is 0 because this block is dropped. So initial velocity is 0. Okay, and then But we do know they told us that the mass of the trolley is m, as well as the mass of the block is m. So here we're actually going to have 2m, and we have this final velocity here. All right, so now they want to know the final velocity, the value of the final velocity. Okay, so if I want to know, so I have 2m, I'm just swapping them around, and I have this mass here. So if I want to know what the final velocity is, it's actually going to be m, velocity of the trolley, over 2m. Okay, so that's just basically a half velocity of the trolley. Okay, so if I have a look here, the answer that corresponds is C. Okay. All right, so question 1.5. Okay, so an AC electric motor has a power rating of 1.2 kilowatts. Okay, so that power rating, I'm just going to write it in watts. So that's 1,200 watts. In 1 minute, okay, so I'm just going to write there. With every information that I get, I just write down. Okay, so 1 minute, that will be 60 seconds. So in 1 minute, the amount of work done by the motor in joule is, so we know that the work done, okay, work done is force times displacement, okay, cos theta. But now we have power here in the mix. And what is power? Power is actually the rate at which work is done. As soon as you hear rate, you know there's a time factor into it. So the rate at which work is done. Okay, so we have power, we have the time, we can work out what work is. Okay, so we have the power, we have the time. The power is 1,200 watts and the time is 60 seconds. So what would the answer be? Okay, 72,000 joule. 72,000 joule. And do we see it? Yes, we see it there. It is D. All right, and then 1.6. We are halfway there. All right, so a car travels at a constant velocity, acceleration is 0, towards a stationary listener. Okay, so the car is moving, stationary listener. The car's hooter emits a sound of constant frequency as it approaches the listener. Okay, so you have a car there. Okay. I don't know why I'm even bothering. So it has a, no, now I'm thinking of an ambulance. It is emitting sound from the hooter. Okay, it is moving towards a stationary listener. So you have a stationary listener there, minding their own business, okay? And as it approaches, okay, if I were to draw the waves, just so to see, if it approaches, it would look something, it would look something like this. Okay, the sound that is emitted. Okay, as it gets closer and closer to the person, the wavelengths actually just compress. Okay, because the frequency is getting higher, the wavelengths decrease. Okay, because you know that frequency is actually inversely proportional. Yeah, so frequency is inversely proportional to the wavelength. Okay, so now what is it saying? Which one of the following statements regarding the frequency? Okay, let me pause. Sorry about that, I was a bit distracted. My husband and son came back early. I told them I'm recording. Okay, cool. So now which one of the following statements regarding the frequency and the wavelength of the sound of the hooter as observed by the listener is correct? So both the frequency and wavelength have decreased. Nuh-uh. If your wavelength has decreased, as you can see here, the space in between is actually getting smaller as it approaches, then it means your frequency has to increase. So both the frequency and the wavelength have increased, not both. See, the frequency has decreased while the wavelength has increased? No. The frequency has increased while the wavelength has decreased? Yes. That is correct. It has to be D. Okay. And then 1.7. Yeah. So the number of excess electrons which will cause a charge of -8 microcoulomb on a sphere is equal to. So if you want to get the number of electrons, so number of electrons, it's actually equal to the charge, okay, of that specific sphere over the charge of an electron. Okay, so they told us the charge of that sphere, which is -8 micro, and we know micro is times 10 to the power -6. And then the charge of an electron that you get at the end of your paper, I keep forgetting it, but the charge of an electron, E, is -1,6 times 10 to the power -19. Okay, so now we are just going to calculate and see what the answer is. Okay. So, -8 times 10 to the power -6 all over -1.6. -1.6 times 10 to the power -19. Whoa. Okay. This calculator, I keep forgetting it does this. Okay. 1.6 times 10 to the power -19. I am not going to count these zeros. Yeah, I need to let me try to set the scientific notation quickly, but if not, I will count the zeros and tell you. Okay, so I couldn't quite get it, but I found a separator, so at least we can count the zeros correctly. So it's going to be 5 times 10 to the power 3, 6, 9, 12, 13. So we have 13 there. Okay, and those are the number of electrons. Okay, and if we see there, it's going to be B. Yeah, things that you need to check with your calculator before writing an exam. You don't want this problem. Okay, now it says 4 identical light bulbs are connected as shown in the diagram below. So if you think of a light bulb, it's actually like a resistor. Okay, so the brighter the light bulb is, it means it has a high resistance. Okay, so yeah, think of it that way. So now it says, how does the brightness and potential difference of L4 compare with the brightness and potential difference of L1? Okay, so allow me to just make some marks over here. So let's pretend we have resistors. Well, a light bulb is a resistor, but you know how we normally indicate resistors? We indicate them, or maybe let me just redraw it. So you have your battery over here, okay, and you have your first light bulb, you have your second light bulb, okay, the third light bulb is here, and then you have the fourth light bulb. Okay, and I'm just going to pretend that each light bulb has a resistance of 2 ohm. I'm just going to use 2 ohm just to simplify it. Okay. And let's say there's a current. You know the current flows from the positive terminal of the battery to the negative side. So you have a current. Again, I'm just going to use 2 just to simplify it. So if that's the case, if I were to look at the potential difference, okay, on the first, so this is number 1, 2, 3, and 4. Okay, now I need to use a different color. So if I were to look at the potential difference at 1, okay, remember voltage is equal to current times resistance, okay, V is equal to IR. So in this case, it will be 2 times 2, so it will be 4 volts. Again, here I'll have 4 volts. Now, because these light bulbs are identical, okay, the way in which the current will separate here, it will be equal. So if I have 2 amperes, it means then I will have 1 passing here and 1 passing there. Okay, so if I'm to calculate the potential difference again, on the third light bulb, I would have 1 times 2, which is 4 volts. Even here, I would have, no, 2 volts. What am I saying? Sorry, guys. 2 times 1 is 2. Even here, I would have 2 volts. So already with the potential difference, we can see that L4 is less, okay? It's less than L1. So we have A and B as our options. Now, looking at the brightness. Okay, guys, so here you have a lot of resistance, okay? So this is resistors in parallel. Sorry, in series. But if you have to look at the resistors in parallel, okay, remember 1 over R parallel. Sorry. So if I were to look at my resistors in parallel, I have 1 over 2 plus 1 over 2. And that would be 2 over 2, which is just basically 1. Okay, so R parallel is 1 ohm. So as the current separates, over here we have parallel resistors, where you have L4 actually, your light bulb number 4, you see that they actually have less resistance. Okay, and if you have less resistance, then it will shine less. Your light bulb at L4 will actually shine less than the one at L1. Okay, I hope that makes sense. So if we're looking at between A and B, we said the potential difference is less, okay, and the brightness as well will be less. Okay, yes, actually we're looking at A and C because we said potential difference is less, but if you look at the brightness, it will definitely be less as well. And I really hope it made sense. So the answer there would be A. Okay, we're almost there, and I'm almost running out of air. Okay, so now 1.9. Like I said, if I keep pausing, it means I'm actually coughing and taking a break to cough. So, which one of the following devices cannot operate with both DC and AC currents? Okay, so in the event that you do not know for a kettle, a light bulb, electric fan, transformer, just think about what you do know and what is actually covered in the syllabus. They actually make it explicit that when you have a transformer, it only operates under AC. Okay, transformer, only alternating current. It does not operate under direct current. Okay, so they, just by knowing the transformer, I go for B in an exam situation. Okay, but like me here at home, you can actually Google. I actually did take the time to Google, and the electric kettle can operate under AC and DC as well as the rest, okay? But obviously it's preferred to use alternating current. But a transformer, guys, please do not forget this. It only operates under alternating current. So not both. So that is B, the transformer. And then the last question, 1.10. Okay, so in an experiment on the photoelectric effect, a scientist shines a green light on a metal surface and observes that electrons are ejected from the metal surface. Later, the scientist shines a blue light with the same intensity as the green light on the same metal surface. So what happened? We went from blue to green. Okay, the intensity is still the same. All right, so intensity, what's the difference between intensity and frequency? Well, basically frequency gives the same amount of electrons energy. Okay, so the higher the frequency, the higher the energy. Remember, according to this equation, that energy is actually directly proportional to frequency. So the higher the frequency, the higher the energy, specifically kinetic energy. And So that's frequency. But intensity, if you increase the intensity of a light, then it means more electrons are coming out. They have the same energy, but more of them are coming out. So here they tell us intensity is kept constant. Okay, but the difference is we had blue light, or we had green light actually initially, and then later on we started with green, right? And then later on we went over to blue. So what is the difference? Yeah. So now I haven't even read the question. It says, which one of the statements below will be the correct observation as a result of this change? So the number of electrons that are ejected will increase. Okay, guys, intensity stays the same. So number of electrons stay the same. So A and B, we don't even look. It's talking about the number of ejected electrons. We will look at C and D. Now the maximum kinetic energy will increase, or the speed of the ejected electrons will decrease. Okay, so you went from green to blue. Remember Roig Bev? So red, orange, yellow, green, blue, indigo, violet. So red here, it has a higher wavelength. Okay, looking between these colors, it has the highest wavelength but the shortest frequency. Okay, when we get to blue, or getting to violet, violet has the shortest wavelength but the highest frequency. So you can see when you go to the left, no, sorry, to the right. If you go to the right, then your frequency increases and your wavelength decreases. So if you're going from green to blue, blue definitely has the highest frequency. Okay, that's what we want to know. When we talk about the photoelectric effect, we're interested in the intensity as well as the frequency. So in this case, we know that the frequency of blue light is actually higher. And what does frequency coincide with? It coincides with energy, kinetic energy to be specific. So the maximum kinetic energy of the ejected electrons will definitely increase. Therefore, C is your answer. Okay. And the speed was also increased. I mean, kinetic energy is equal to what? Half mv squared. So D cannot be correct. All right. So we are done. I can go and breathe and cough and do whatever, and you guys are understanding. So thank you so much for tuning in. Please don't forget to like our videos, subscribe to our channel. Please tell your friends about it. Those who are doing maths and physics, to also come and tune into our channel and learn. Okay, and also one request, please also show your parents our channel so that they see if ever they're looking for a tutor for their kids, for you, then there's content backing us up. All right, so yeah, enjoy the rest of your day or evening or morning, and it is bye from me.
Well, good day to you. I hope you're doing well. Welcome to MV Tutors. My name is Figa. Now, first of all, we are doing the prelims, the Gauteng prelims 2021 September. We just wrote this, I think, a week or two ago. So this is the memo explained in a more digestible way. Okay, so please remember to like and subscribe this video so that more and more students could have access to it and get the help that they need. And also, secondly, if you need extra help after this, like you need a tutor, I'd be glad to be your tutor. But I would like to caution you that please involve your parent or your guardian in asking for a tutor. So show them this video before you actually consider contacting us for tutorial, because remember, the parents and the guardians, they are the ones who are paying the fees, and we charge a fee to tutor you. Okay, so make sure that before you contact me, that you actually speak to your parent first. Okay, right, well, let's get right into it. Okay, so it says an empty lift is supported by a steel cable. This is question number 2. You've already done question number 1 with my wife. The lift moves upwards at a constant speed while an upward force of 2,500 newtons is applied by the cable. Ignore the mass of the cable and all frictional forces. Okay, number 1, state Newton's second law of motion in words. Now, you should be knowing this, but I wouldn't like to assume that you do, okay? Even though for the fact that you're watching this, it means at least you're in grade 12 and you should have done this over and over. However, I will give you a clue on how to remember Newton's second law. So, force is equals to mass times acceleration. This is Newton's second law. We need to be able to put this in words. But in order to put it in words, I'm just gonna make acceleration the subject of the formula. And then you're gonna have F divided by M. Okay, and then in putting this in words, then you would say when a resultant force acts on an object, okay, the object will accelerate in the direction in the direction of what? The direction of the force. That's number 1. But you don't just end there. Remember, I told you that this is the clue. Okay, now you need to be able to then speak about the actual force, like the actual acceleration. Okay, the direction of the force, okay, at an acceleration. Okay, so what about the acceleration? The acceleration here, if you look here, the acceleration is directly proportional to the force and okay, when it comes to the mass, as you can see, the mass, it's indirectly proportional, so we'll write that in words. And indirectly, or don't put indirectly, put inversely. Proportional inversely proportional to the mass. To the mass of the object. Okay, so that's it. That's all you have to do. Right, let's go get the second question now. It says draw a label-free body diagram indicating all forces acting on the lift while it is traveling upwards at constant speed. Okay, it's not bad. So we are now on question 2.2 and we're gonna draw this. Okay, so there are two forces here. Okay, we've got this one. Okay, and then let's say the object is here. We've got this force going up Okay, and this force is let's call it the tension force. Okay, this is the tension on the cable. It's going up, and then we've got another force going down. Maybe let's give it a different color, but this one is going down, like just like that. Okay, and this is what we call the force due to gravity, Fg. These are all the forces that are acting on this thing. All right, yeah, that's it. Now let's continue. It says, write down the magnitude of acceleration of the lift as it moves upwards. Okay, we are now in 2.3. Well, as it moves upwards, we've been told that actually, if you look at this question here, they told us that this thing moves at constant, okay? I don't want to cancel it, I want to underline it. It moves at constant speed. Now, if you know your theory, you know that if something is moving at a constant speed, that means acceleration is therefore 0. Acceleration is equals to 0. Well, you can put the units, but it's equals to 0. Okay, so let's do 2.4 now. We're gonna go ahead and change our color. Let's go yellow. 2.4. Okay, 2.4 says calculate the mass of the empty lift. Okay, so very easily we know that the force of gravity is equals to mass times acceleration, right? And we know that the acceleration is actually the gravitational acceleration, so that's g over there. Now the force of gravity, we actually have been told here that it is actually 2,500 newtons. Okay, so we're going to put 2,500 to this side. All right, and the reason they are equal, well, actually this is the upwards force, but it's gonna be equal to the force of gravity, so it's fine like that. And then we'll put the mass, and the gravitational, you use 9.8, sorry. So let me just bring this to the middle, give us more space to work with. Okay, so to get my mass, then it will be 2,500 divided by 9.8. Well, ladies and gentlemen, let's get a calculator at this point. There we go, we got our calculator right here. So we're gonna say 2,500 divided by 9.8. So that's 255.10. Thank you so much, calculator. So it's 255.10, and the unit of mass is, well, let's see, what are we giving it? Okay, it's kilograms. It's kilograms. It's kilograms because it's 9.8 and there's 2,000 newtons. So mass will always be in kilograms, not grams. Please don't make that mistake of thinking it's in grams. Okay, all right, let's move on to 2.5. It says when the 2,000 Newton force of the cable is replaced by a force of 3,000 newtons, the lift accelerates upwards. Calculate the magnitude of this acceleration. All right, so let's do this. This is now 2.5. So what we have here is that 3,000 replaces the 2.5. So that means we have a disparity now. Now, tension is no longer equals to the force of gravity. Okay, there's a difference, and that's gonna be equals to ma. Remember, this is coming from force is equals to ma. So the force, this is the net force, the resultant force. It's tension minus force of gravity, and the tension at this point therefore is 3000 minus the force of gravity is still 2.5, and that's equals to the mass, which we just solved to be 255.10, and then what we want to solve for is the acceleration. Okay, so here what I'm going to do then is I'll make A the subject of the formula. So 3000 minus 2500 is simply 500, and then divide by 255.10. Let's get our calculator at this point. Okay, so what do we have here? We have 500 divided by 255.10. That's equals to 1.96. Thank you so much, calculator. That's equals to 1.96. This is our acceleration. Acceleration is always in meters per second squared. Okay, that's it. Now let's go to question 2.6. Question 2.6 says, identify the force that forms a Newton's third law force pair with the weight of the empty lift. Well, this just means what other force can we consider that is at play here in this question. Okay, so we can say then in 2.6, sorry, we can simply say it's the force of the empty lift on the planet Earth. Okay, let's write that down. The force of the empty lift on planet Earth. I know it sounds silly, but remember, we are still on Earth. Right. Anyway, I hope you understood everything that we just did, but in the event that you didn't, do contact me. I would love to be your tutor. You can contact me through my website, www.mvtutors.co.za, or alternatively, you can just WhatsApp me on 076 312 1107. And remember, involve your parent.
Hello everyone and welcome to MV Tutors. I'm Tselo and I'll be looking at question 3 with you guys from the prelim that was written not so long ago. Okay, so yeah, physics paper 1, question 3. Let's get right to it. So it says a boy standing on a bridge projects a ball A vertically upwards with an initial velocity of 5 meters per second. The height of the bridge is 20 meters. Ignore air resistance. Okay, so let's just say this is the bridge. Oh yeah, and that's where the boy is standing. Okay, and he projects a ball from the bridge. They actually didn't tell us where the ball is gonna end up. It could end up on the bridge or it could end up on the floor, wherever the floor is. Okay, so yeah, and that is our bridge structure over there. So now 3.1, give the magnitude and direction of the acceleration of ball A as it leaves the boy's hand. Okay, so we know that with vertical projectile motion, the acceleration actually that affects your projectiles is gravitational acceleration, and the value of that, or rather the magnitude, is 9.8 meters per second squared. Now, gravity is always acting downwards, okay? The earth is pulling all the objects on it and the people and everything else downwards, okay? So, therefore, we have downwards over there. And now for question 3.2, it says calculate the total time it will take for ball A to reach the road. Okay, so now we know this is the road. Okay, so yeah, what is happening there? What is my strategy in calculating the time? There are many ways of doing it, but I'm gonna take it in sections. Okay, so I'm gonna calculate the time it actually took to actually reach upwards. I know I'm gonna take upwards as positive. You can take downwards as positive. We're gonna get the same answer. So if I take upwards as positive, it means the initial velocity here, which was 5, is going to be positive 5, okay? Until it reached a maximum height where the velocity there is 0. Okay, and at that same level where the ball was thrown, okay, remember as the projectile goes up, the velocity decreases until it gets to 0, where it actually changes direction and then heads downwards. Okay, so as it heads downwards, from the level with which it was thrown, that velocity will be the same. Okay, so I'm going to get a velocity of 5 this side, but because I took upwards as positive, and this time the ball is going downwards, this velocity here will be negative 5. Then it will reach the ground or the road, where now you'll have your maximum velocity. And one thing to bear in mind, they told us that the height of the bridge is actually 20 meters. Okay, so that will actually help us. So now the time it took from the bridge to reach its maximum height, that will be T1. And that time it takes from the maximum height to the same level at the bridge, that will be T2. And if you remember well, those times are going to be the same. Okay, and then from the bridge all the way to the road, that is going to be time 3. So that is my strategy here. Okay, so let us begin. And then we're going to have to consult our equations of motion to actually see what formula to use. Okay, so for time 1 and time 2, I have my initial velocity, which is positive 5, and I have my final velocity, which is 0. So I'm going to look for an equation that needs final and initial velocity, and that's not complicated as well. So I see the first equation there. Actually, I can use this one. All right, so there I have the final velocity is equal to the initial velocity plus acceleration delta t. My final velocity is 0. My initial velocity is positive 5. And acceleration, because it's always acting downwards and I chose upwards as positive, I'm going to have to use a negative here. If you chose downwards as positive, then you'll have a positive 9.8 and your velocity will be negative. Okay, so just be aware. Okay, so if I then make delta t the subject of my formula, I will then get negative 5 when I take it to the other side and negative 9.8. Okay, just going to use our calculator there. So we have negative 5 over negative 9.8. And that answer there is 0.51 seconds. Okay, don't forget your units. So I have 0.15 seconds, and that is equal to T1, which is actually equal to T2. And now we can solve for T3. So what happens there with T3? I have my initial velocity, which is negative 5. I don't know what my final velocity is. I'm not going to take the route of calculating the final velocity. I'm just going to get an equation where I only need initial velocity as well as displacement. Okay, and if I look, I actually see this one, delta y. That equation will actually work. So we have delta y is equal to initial velocity times delta t plus half a delta t squared. And actually this delta t is going to be my t3, right? Okay, so because we chose upwards as positive, this ball is now moving in a downwards position. So from the top of the bridge to the road, it's actually going to be negative 20. Okay, so negative 20. And our initial velocity, that will be negative 5. Okay, and I'm just going to put in t3. All right, and we have a half there, right? And we know that our gravitational acceleration, actually, let me just put a positive here. So it's going to be a positive, but because gravity is acting downwards, I'm going to have to put in negative 9,8 there and delta t squared. So now we have a quadratic formula. Let me just put it nicely. So now I have 9,8 over 2. I forgot I'm using T3 now. Okay, that's T3. So 9,8 divided by 2, T3 squared. Okay, then I have positive 5, T3, and I have minus 20 is equal to 0. And at this point, you can use your quadratic formula, where actually the subject of your formula or your unknown is T3. Okay, then we have negative b plus minus b squared minus 4ac, all under the square root there. And we know that the value for a is 9,8 divided by 2. The value for b is 5, and the value for c is minus 20. Okay, so now let us solve for it. I'm actually going to use a quicker way. I'm going to use the calculator. So for those who have calculators that can solve and you want to save time for very challenging questions, you can use a solver. So if you want to solve a quadratic equation, okay, so for the value of a, like we said, it's 9,8 divided by 2. So yeah, 9,8 times a half. That's value for a. And the value for b is positive 5. The value for c is negative 20. And then we get our solutions. We get negative 2,59. Okay. So you know that a time cannot be negative, so that is not a solution. And then on the other hand, we get 1,57. Okay. So now, having a look at, wow, this question was long. How many marks is this? Okay, it was 4 marks. Okay, maybe I'm just taking my time. So T1, we get 0,51, T2, 0,51, T3, 1,57, I think. So it will take the, we just need to find out what the sum of all those times is. Okay. And then get the total time. So the total time will actually be equal to 2 times 0,51, because time 1 and time 2 are equal, plus 1,57. And let's just see what that equates to. Okay, so we have 2 times 0,51 plus 1,57, and our answer is 2,59 seconds. That is the total time it takes. Like I said, you can do it in many other ways. I just chose one where you can actually see what is happening, and also just a reminder for you of what happens when you throw a projectile from a position and it lands up in the same position, that the velocities are the same as well as the times. Okay, now let us head over to 3.3. So here they've actually sketched for us what is happening. We had A go up with an initial velocity of 5. And now they tell us there's B. Okay, but let's read. So it says, at the same instant that ball A is thrown upward from the top of the bridge, another ball B is projected up from the road. Ball B has an initial velocity of 14 meters per second. Okay, now they're asking, calculate how far apart ball A and ball B will be after 1,2 seconds. Okay, so again, referring to our equations of motion, we're going to see the formula where we have delta y. Okay, so 1,2 seconds they said. So the equation where we have delta y, okay, I'm gonna go with the one that just has initial velocity. Okay, I don't want to play with the final velocities here. Okay, so it's the same one that we used previously. It is going to be delta y is equal to initial velocity times delta t plus a half acceleration delta t squared. I will be using this equation for both these questions, or rather these balls. Okay, so for A, let's just see how far it is at that point. So we have initial velocity of 5 and 1,2 seconds. So we have a half there. This ball is going upwards. So gravity has to be negative 9,8. And then we have delta t squared. Okay, so 1,2 squared. And then let's just take out our calculator. Okay, plus a half, negative 9,8 times 1,2 squared. Okay, so we have a value of negative 1,056. Okay, don't be scared if you see a negative. Let's just see what's happening here. So what I have done, I know that for it to reach its maximum height, there's actually a time of 0,51 seconds. So once it gets to the other side, where it's actually going down, I'm expecting to get a negative answer. Okay, because now it's facing downwards. All right. So, oh, look at me using seconds. I actually have meters there. So yeah, so basically this negative 0,1056 meters, it's actually telling me that from the top there, okay, to actually get to whatever point I'm getting to. So the value there will be negative 1,056. Okay, so let's just see. Okay. Yeah, what I actually wanted to check. So we know that for it to reach its maximum height, it took 0,5, where's that value? 0,51 seconds. So if I take 2 times 0,51 seconds, it's actually 1,02. Okay, let me go back to my sketch. I hope I am not confusing you guys. Like I've managed to confuse myself a bit. But the whole time that it took for it to reach its highest and back to the bridge, we actually said that it is 1,02 seconds. Okay, but now this time here it's 1,2 seconds. Okay, so we're looking at the value here that we got, that negative 1,056 meters. That's what you would subtract from the 20. Okay, so it has reached this point over here. Okay, so actually ball A, if we use the bridge as a reference, okay, the bridge there leading to the road, that is actually 20 meters. So ball A is somewhere here, okay? And at that point, it's going to be 20 minus the 1,056 meters, okay? Because that is the negative 1,056 meters, okay? So that value there will actually be, let's just say 20 minus 1,056. So that's 18,944. At this point, I'm not really rounding off to 2 decimal places. Only my final answer will I round it off to 2 decimal places. So ball A is actually 18,944 meters above the road. Okay, so that's the position of ball A. Yeah, I hope I didn't lose you guys there. If I did not know the time it took for the ball to reach the maximum height and all the way down, I wouldn't probably know where this negative 1,056 applies to. Okay, so it helps to know. Okay, now what happens for ball B? Okay, so its initial velocity was 14, and we have 1,2, then we have 1.5, and again it's thrown upwards, so negative 9,8, and then 1,2 squared. Okay, so let's see how high up this ball is. So we have 14 times 1,2 plus a half, negative 9,8, and then multiplied by 1,2 squared. Okay, so that is 9,744. Okay, 9,744. So above the road. Okay, so I'm just going to say this is above the road, and this is below the bridge. Just referencing. Okay, so now ball B, somewhere there. Okay, and now I want to know how far apart ball A and ball B are. Okay, so if you're gonna, we want to actually get this distance in between ball A and B. How far apart, right? Yes. Okay, so we're actually going to have, let's say, distance between A and B. Okay, so we had 20, okay, and we said that ball A is 1,056 below the bridge. Okay, now let me just do it like this rather. Ooh. Okay, sorry about that. Okay, so yeah, distance between A and B. I'm actually going to take the 18,944. I forgot that I actually had it. So 18,944. Okay, that's the whole distance here, the 18,944, and I'm going to subtract it by the 9,744 so that I can get the distance in between. Okay, so 18,944 minus 9,744, and the answer is 9,2 meters. Okay, and that was a nice 6 marks. You really had to think about it there. All right, and then 3.4, the last question. Now it says, draw a velocity time sketch graph for the motion of ball A from the time that it is projected up from the bridge until the time it rebounds to a maximum height. Okay, there's one thing I forgot to read, and this always happens to me. I get into such a rush into reading the questions that I forget that there's actually information given. So now it says tennis ball A hits the road below, stays in contact with the road for 0,2 seconds before it bounces up with a velocity of 14 meters per second. So we had the bridge there, remember? This ball went all the way up, and then it went to the road, and then it bounced. So there was some time lapse there, and then it bounced. Okay, so actually no, let me do it a little bit better. Okay. So it went all the way up, down to the road, bounced, and went up again to reach its maximum height. We know the velocity there was positive 5. The velocity there is 0. Okay, the velocity at the ground, we did not work it out. We can, really, it's possible. Okay, and then we have the velocity there, which is 0. But remember, the velocity with which it hits the ground, we don't know it. But there was a time lapse here of 2 seconds, so it's 0.2. A time lapse here of 0.2 seconds, where now the initial velocity, when it goes up, they actually gave us as 14 meters per second. And now they want us to draw the sketch, okay, not the free body diagram, but the velocity time sketch. Okay, and we need to indicate the following: the initial velocity of the ball, the time when the ball hits the road and is in contact with the road, and the velocity of the ball when it rebounds from the road. So they gave us the velocity that it rebounds, which is 14 meters per second. If you wanted to work out the final velocity here, we can actually work it out, né? For those who just want to get to the answer, you can fast forward. For those who want to know how they would work it out, yeah, let's do it. Let us do it. So you have final velocity squared is equal to initial velocity squared plus 2. Should we use that one? No, I don't want to use that one. Sorry. I will use the one with time. Let me see. Yeah, so final velocity is equal to initial velocity plus a delta t. Remember, we know the time it takes from the maximum position to the bottom. Okay, so our initial velocity is going to be 0 because we're taking it pretty much from here. So initial velocity is 0, and the acceleration is going to be negative 9.8. No, actually now we're going down. Okay, so it's just going to be 9.8 because we are going down. All right, and then delta t, remember it took 0.51 seconds there, and the rest of the time it took 1, something, 1.57. Okay, so that actually the time there, it would be 1.57 plus 0.51 seconds, that's 2.08. So I have 2.08 there. So our final velocity when it reaches the ground, 9.8 times 2, times 20.38 meters per second. Okay, but then when it rebounds, it's now 14 meters per second. What happened there? It lost some velocity when it was in contact with the ground. Well, one way of explaining it is it came with a lot of energy, right? Okay, remember kinetic energy is directly proportional to the velocity. So once you reach your maximum velocity, you actually have quite a lot of energy, and that energy will be transferred. You know, when you bounce a ball, you hear a sound. So the energy is transferred to sound. Also, the ball, when it gets into contact with the ground, it like deforms just for a moment. Okay, so the energy is also transferred to that deformation. Another thing is heat. You know, if you keep hitting a ball on the ground and you actually check the temperature of a ball, you'll find that it's actually much warmer. So the energy lost there due to sound, deformation, and heat. That is why then your initial velocity as it rebounds is actually less and not more. So it went from 20.38 to 14. Okay, remember, this is just extra information. This is not what's required for you to draw. Okay, so finally we can then draw. Let's go back to question 3. Yes, we can then draw the graph. Okay, so we have our y-axis here, which would be the velocity. And we have our, let's put it somewhere there, x-axis, which would be our time. Okay, what did I do now? Okay, so we have velocity here, which is meters per second. That's where it's 0. And we have our time here in seconds. So initially, right, it was at 5 seconds. So maybe let me just do it somewhere here. Okay, it was 5 seconds. Okay, and then let me just draw it for you again. We had it there at 5, then 0, then it reached 20,38, then there was a little space, and then 14, and came up again to 0. Okay, so we started at 5, and then we go all the way to 0. Okay, and then from 0, okay, then from 0, remember, 0 indicates where it reaches its maximum. So this was 5, and that is 0. And then here we had 20,38. Okay, so that value there, 20,38. Then it came into contact with the ground. Okay, so that we indicate, let me just erase all of this for now. That we indicate with a dotted line. Okay, so from this position here, this is very exaggerated. This is your 0,2 seconds. Okay, so then you have your normally indicated with a dotted line. Okay, that didn't look so nice. Say that's 14. Okay, and this space that I have here, that's actually the 0,2 seconds. That's why I say it's very exaggerated. Okay, but just bear with me. So that value there, 20,38, but it rebounds, guys, and they gave us the rebounding velocity, which is 14. So right over here, we are going to get 14. And at this point, then it goes back to 0. Okay, because as it reaches its maximum height, that's where velocity is 0. And the thing about the velocity time graph, so this line over here actually will be parallel to this line over there. Okay, the lines are actually parallel, but we're not drawing this to scale. They're not marking you on the how good your graph looks. I'm just saying in general, they're parallel lines. Okay, so now what do they want? They want us to indicate the initial velocity. That was 5. And then this time here, remember that was 0,51 seconds. They didn't ask us for it. I'm just putting it out there. And where it reached its maximum, its maximum velocity at the road, we calculated it to be 2,59, remember? So that's 2,59 seconds. Then there was contact with the ground, with the road, for 0,2 seconds. So 2,59 plus 0,2, that's going to be 2,79 seconds. And then it rebounded from 14 meters per second until it reached its maximum height. Again, they don't need us to calculate the time at the end. You can do that, guys. You know your initial velocity. You can do it using this formula. You know your initial velocity. Okay, let's just do it. People can just stop the video here. So your final velocity, you know it is 0. Your initial velocity, it is 14. Okay, at this point, it is going up. So you have negative 9,8 and you have delta t. Okay, so if we have, so delta t would be negative 14 over 9,8, negative 9,8. So negative 14 over negative 9,8, that is 1,43 seconds. Okay, so you're gonna take the 2,79 plus the 1,43 seconds, and that's 4,22. So it would reach there at 4,22 seconds. And yeah, we did more than was actually asked, but I hope that you really understood this question. This is where you can actually collect your marks, and you really should. So I hope you learned something. Please do communicate or share this information with your fellow matric, learner friends, your teachers, even your parents as well, especially if you'd like for us to tutor you. And yeah, do like our videos and subscribe to our channel. Thank you so much for tuning in. Bye. Hello everyone and welcome to MV Tutors. I'm Solo and I'll be looking at question 4 from the physics paper 1. Okay, so it says a car with a mass of 900 kilogram is moving east and collides with a freestanding barrier that has a mass of 3,200 kilograms. So let's just pretend that that is the barrier, something like a wall. And you have the car, by the way, it's standing, right? It's not moving, so the velocity is 0, but the mass is 3,200 kilogram. And then you have a car that is moving east. Okay, so let's just say that's our car. Okay, it is moving east. Okay, it has a velocity of, okay, we don't know what the velocity is. But its mass, it is 900 kilogram. Okay, so it goes and it collides with this freestanding barrier. Okay, so what happens? Is it going to collide with it and they become one, or is it going to collide and rebound? Let's see. So study the following momentum time graph of the car and the barrier below and answer the questions that follow. Before we even answer the questions, let's just look at this and see what is actually happening. So this is for the barrier. Okay, I'm just gonna, okay, that's where the barrier is. And the first graph here, that's for the car. Okay, so we can see that initially its momentum is 18,000. Okay, so that's something we can put there. Momentum initially is 18,000 kilogram for the mass per meters per second, or meters per second, which is the velocity. Okay, and we can see that initially the barrier has a momentum of 0, and that makes sense because it's not moving. Okay, so it has 0. And then there's a collision. So the collision happens somewhere around here. Okay, and we can see that the car, it rapidly decreases. Okay, the momentum rapidly decreases. Why? Because once it collides with the barrier, its speed is going to rapidly decrease. Okay, it decreases to such a point where this at the bottom here, it actually indicates that it rebounded. Okay, it went into the opposite direction. So we know that the final momentum is actually negative 144 kilograms meters per second. And on the other hand, the barrier, it probably moved. Okay, it did move, or else the momentum would still be 0. So it increased rapidly from 0 all the way to 18,144. Kilograms meters per second. Okay, and you can see there was an exchange of energy from the car to the barrier. Okay, so now let us get to the questions. Okay, so 4,1, State the law of conservation of linear momentum in words. Okay, so basically, yeah, the total linear momentum of an isolated system is conserved. Okay, because the system is isolated, it will be conserved. All right, you could also say it remains constant. Okay, and now 4.2.1, use the information given on the graph to calculate the final speed and direction of the car. Okay, so our momentum before and our momentum after, well, the two objects, the car and the barrier, they are still separate before, and they're separate before and they're still separate after. So yeah, we can just see what is the mark allocation, 4 marks there. So the momentum before of the car, okay, that's just going to be mass times velocity. So we know that before it had a momentum, or initially it had a momentum of 18,000, the mass there 900. So just to see the initial velocity, how much that is. So 18,000 divided by 900. Well, if we cancel the zeros, we're left with 180 divided by 9, and that will be 20. So that's 20 meters per second. So it came in with 20 meters. That's very fast. So 20 meters per second. Remember, it's not 20 kilometers per hour. That's just 20 meters per second. Okay, that's a lot. But we're not done. They didn't ask for the initial velocity. They asked for the final speed of the car and the direction. So we have the momentum before, the momentum after, however, still mass times velocity. We know that they ended up with 144, negative 144, okay, kilograms meters per second. The mass is still the same, and we have the final velocity. So the final velocity would be negative 144 over 900. And we definitely need the calculator for that. So negative 144 over 900, that is, no, 900. That is negative 0.16. So low. Okay, so if we were to interpret that negative, remember it was initially going east toward the barrier. So then it's going to be it's going to be 0.16 meters meters per second west. Sorry, I'm writing like we did in varsity, so this is like a high school way of writing. Okay, so 0.16 meters per second going west. Okay, so it did rebound, and the velocity then, or the speed, was actually much lower than it was initially. Okay, and now they want the impulse of the car. Okay, so if you've forgotten what impulse is, you can go and check your formula sheet. I actually haven't checked if they have it, but they should. So what is impulse? Impulse is the change in momentum, okay? And we can actually see it here under the force heading, first, second, third row, okay? So impulse, which is change in momentum, you could say I or delta P. Okay, that's equal to the net force times time. All right. And then the net force, net force is actually equal to mass times acceleration. And then you have time. Okay, acceleration, that's actually meters per second squared. And time is actually measured in seconds. So if we cancel out, we're actually left with meters per second. So actually, that would be mass times velocity. But the change in velocity. All right, so that is impulse. Now let us get to, now they want the impulse of the car. So we know the mass is 900. The final velocity is 0.16. Put the negative sign there. And the initial velocity is actually 20. All right, and then final answer. Sorry about that. 900 negative 0.16 minus 20. Okay. So it's the same as the wall. The final, what is it? The momentum after, so the final momentum. So negative 18,144. So since it's impulse, it's going to be kilograms, meters per second. Okay, so that is the impulse on the car. Or with this negative, you could interpret it to say west, because negative actually indicates west, whereas positive is east. Okay, and then 4.3. Okay, it says, is this collision elastic or inelastic? Now, what is the condition for something to be elastic? Well, basically, the sum, not the change, the sum of the kinetic energy, okay, initially has to be equal to the sum of the kinetic energy finally, or before has to be equal to after. Okay, if the sum of the kinetic energies is not equal before, initially, or afterwards, then it is not elastic, it is inelastic. Okay, so yeah, is this collision elastic? Well, we're gonna take the sum of the kinetic energy of the car and the wall before, and then take it again for the car and the wall afterwards, and then we'll see. Okay, so I'm just gonna say before. Okay, so I have half m for the car, velocity squared for the car, and I have half m of the, what should I call it, a wall, a barrier. Okay, I'll just say B. Mass of the barrier, velocity of the barrier squared. Okay, so we know initially we had 900 kilograms, so we still have it, and the velocity initially was 20, but here it's going to be 0 because initially the velocity was 0. Okay, so the kinetic energy, or the sum of the kinetic energy before the collision occurred, that would be equal to 180,000. And what would the unit be? Joules, because we're dealing with energy now. All right, now let's have a look at after. Okay, so again we have half the mass, 900, and the final velocity, it was negative 0.16 squared, and then half the mass was 3,200, and the velocity, okay, I actually do not know the velocity of that. Okay, so it's okay, so the momentum of the the momentum of the barrier is 18,144. Okay, so we had what? 18,144. That was P. Okay, it's mass 3,200, and then we have velocity. So velocity, yeah, we're calculating things quick on the side. So 18,144 divided by 3,200. that is equal to 5,67. Okay. All right, 5,67 meters per second. So that's the final velocity, right? So the final velocity, 5,67 squared. Okay, now let us calculate everything. So I have 0,5, 900, and negative 0,16. Squared, which is 11,52. And then I have 0,5, 3,200, 5,67, and that is squared. Okay, and that is 51,438. What did I do? 51,438,24. Okay, so finally 11,52. So that is now 51,449,76 joules. Okay, so clearly, guys, the sum of the kinetic energy before or initially is not equal to the sum of the kinetic energy afterwards. Okay, therefore the collision is inelastic. Inelastic. Okay, and I think we are done. A nice 15 marks. Question 4. Please don't forget to share with your friends, fellow metric friends, learners. Also share with your parents, share with your teachers as well. Yeah, just keep sharing, guys. Share knowledge, okay? And I hope you've learned something. Please don't forget to like our videos and subscribe to our channel. Thank you.
Well, welcome to MV Tutors. My name is Figa, and I will be your tutor today. Well, we are doing the Gauteng prelims, and we are on question number 5. Please do like and subscribe to this channel so that more people will have more access to this content, especially if you are here in Gauteng. This is for you. Now, I would love to be your tutor as well if there's something you won't understand as we go on. But before you contact me to be your tutor, please speak to your guardian or your parent and show them this channel. Show them that we are credible and we are here and we would love to assist you. The reason you do that is because, remember, your guardian or parent is the one who's going to pay for these sessions. So do speak to them first. Okay, otherwise let us get right into it. Question number 5. A 2 kg trolley is at rest on a horizontal frictionless surface. A constant horizontal force of 8 newtons is then applied to the trolley over a distance of 3 meters. Okay, we can see that right here. They showed it. At point A, where's A? There it is. What's happening there? In the diagram above, the force is removed. Okay, the trolley moves a distance of 7 meters up the incline until it reaches a maximum height of, well, they don't say what the height is, but they do tell us that it's at point B. Okay, that's the maximum height is at point B. The trolley experiences a constant frictional force of 1.5 while moving up the incline. So there's a frictional force here on the incline. Cool. Right, now they say define a non-conservative force. Well, you should know this by now, but I wouldn't want to leave anything to chance, so I will not assume you know this. So I'm just gonna define it. Well, it is the force for which, okay, for which the work done in moving an object between 2 points depends on the path taken. Okay, so here you can see the path is straight here, and then it then becomes inclined. So this just basically means there's different formulas you apply to each. Basically, that's what I can say. All right, so let's move on to the next one. Draw a label free body diagram indicating all forces acting on the trolley as it moves along the horizontal surface. Okay, so here we are talking about the horizontal surface. If you look closely, what's happening here? The forces that we have there, let's just change color a little bit. Let's go yellow. This is now 5.2. The forces that you have here, you have one force. Okay, let's start with the 8 newtons. Okay, so you've got 8 newtons going that way. That's gonna be the one force, and we'll just call it force F. Okay, and then you've got another one. Remember, this is a mass, so it's got gravity acting on it, so we're gonna put the force of gravity like right there. So this is the force of gravity. Okay, and then finally we have one more force moving upwards. Okay, we've got this force moving upwards. Okay, and then this force, if you said it's the force, the normal force, then you are correct. So this is what we have. This is the free body diagram for this particular question. Okay, so now let's move to the next question. Let's go see what's happening in the next question. It says, state the work energy theorem in words. Wow. Okay, so again, you should be knowing this by now, but I don't want to leave anything to chance, so I'm just gonna state it for you in words. Well, the net work done, how do you spell work done on an object is equal to the change, okay, the change in the object's kinetic energy. Kinetic energy. Well, for you to remember this, well, basically you just have to go to the formula sheet. It's basically this. So work, where is it? There. You see that? So the net work done is equals to the change in kinetic energy right there. All right, right there. That's it. That's just it. That's what you have to say. Okay, this is in your formula sheet anyway, so you can always come there and just define it that way. All right, see the next question. It says use energy principles to calculate speed of the trolley when it reaches point A. Okay, so remember I said to you there are different formulas to be used. Okay, so at this point, okay, we'll use a particular formula. Speed of a trolley, it depends on the path taken. So the path here, let's go to the formula sheet to see which formula we can pick. Okay, so from the formula sheet here, we will pick this very same formula where W net is equals to the change in kinetic energy. But under there, for work, okay, let's just write it down first. Let's do this step by step so that you are absolutely sure what we are doing. This is 5.4.1. So what we have, I said first we'll take the W net is equals to the change in kinetic energy. I need to rewrite that. So kinetic energy is E energy and it's kinetic. All right, now let's go define W net. We go back to the formula sheet. W net there. Sorry, you can't see that pen. It's W net is equals to force, change in force times the cos of theta. All right, let's go back. So we're gonna write that then. F net is equals to force. Okay, that's the change in force. Okay, or F change in force, or force times the change in what did we have there? We had a change in x. Gotta see it again. It's force times change in distance cos theta. Okay, so change in x there times cos theta. Okay, that's F net. Now kinetic energy, we need to go pick a formula for kinetic energy. There, this one, it's half mv squared. Okay, so we will do that. But change in kinetic energy, if you look here, we'll start it here, we'll start here. Okay, I don't want to cancel that. Change in energy, we'll start here. The change in energy is final kinetic energy minus initial kinetic energy. So let's put that rather first. So we said it is energy kinetic final minus energy kinetic initial, and then remember we had half mv squared, so it's gonna be half mv, and this is the final one squared minus a half mv initial squared. Cool. Okay, let me rewrite this one nicely over here, changing in x, and then we have cos theta. That's the angle we're dealing with. Right, so now we have everything we need. We just need to plug and play now. So let's start with the force. Okay, so the force we have is this 8 kilonewtons. Okay, so let's just put that down. I want to write it in white. So that's going to be that 8. Okay, and then what's going to be my change in x? So my change in x is the distance. Okay, so if you look at that distance here, it's 3 meters. So we're gonna put that 3 in brackets there. Okay, and then we have cos. Now what's the angle there? The angle there is basically 0. There's no angle of inclination. So we got half, and the mass of this thing, they told us the mass of this thing. They said the trolley is 2 kg right there. So we know that m then is 2, and then the final velocity, that is what we are looking for. So squared minus a half, m is still 2, but initially, remember, this thing is in it's at rest. They told us here they're at rest. Okay, so if it's at rest, that means velocity is 0. Okay, so when we come here, we will just put a 0, which makes the entire thing 0. From here, it's just a matter of doing some mathematical gymnastics. Okay, in that I mean that 8 times 3 is 24. Cos 0 is 1, so it's 24 times 1 is equals to, these 2's cancel each other, so I'll be left with v f squared, and this is just gonna be 0. Anything multiplied with 0 is gonna be 0, so I'm not gonna even bother putting that in a calculator. And then to get rid of this square, I have to introduce a square root on both sides. Okay, so therefore my vf, my final velocity, then is square root of 24. Let's get a calculator real quick. Let's see what the square root of 24 is. Square root of 24, that's gonna be equals to 4.89. okay, 2 decimals, it's like 4.90. Thank you so much, calculator. 4.90, that's our answer. 4.90, and the units for velocity is equals to meters per second. Now, what's the difference between speed and velocity? Speed is a scalar and velocity is a vector quantity. That means that speed, you only give the answer like this without any direction, but a vector quantity, which is velocity, then you have to include the direction. But because they ask for speed here, we don't need to include direction. Okay, so we'll just leave our answer like that. Cool. All right, now here they say they are looking for, actually they're looking for the height of a trolley, actually the height of that trolley when it reaches the point B. And the point B, if we look up here, we're going to find it up there. There's the point B. So remember, non-conservative force, it depends on the path taken. So we took a straight path here, but now we're going on an incline. Okay, so the formulas will be different. Okay, the path is different. So let us do this. We'll do it in B. We're doing 5.4.2. okay, so now let's go to our formula sheet to see which formula are we going to pick. Well, the one that we have to pick at this point is this one that includes friction. Okay, so let's start by writing that down and then we'll take it from there. So that was W, and we have a NC there, and then that was equals to a change in potential energy. It's not written like that. It's energy and it is potential plus the change in energy, but it is a kinetic. All right, let's go further then to define them individually. So what we'll do, change potential energy. Potential energy is given by this formula right here. You can see there, even though I've cancelled it, but it's mgh. Okay, so under here we're gonna write the change in mgh, okay, plus kinetic energy. If you remember, it's still a half mv squared. Okay, that's cool. Now let's come to define this one here. Let's go back to our formula sheet. It's still f, a change in distance, cos theta. All right, so it's, what was it, f, and then we had change in distance and then cos, I don't know why that just happened, cos theta. All right, I think we pretty much almost have all we have, everything we need, but we need to do this. Okay, so change in mgh, this means that this is the mgh final minus the mgh initial. Okay, so that's gonna be plus, also this side it's gonna be the half mv squared final minus the half mv squared initial. That's it. It's still gonna be f, change in distance, and then cos theta. All right, let's start filling this up now. What is our force? Well, let's come see if we have it here. Our frictional force we've been given is 1.5, so we're gonna put 1.5 under there, under F. It's gonna be 1.5 times change in distance. Let's go check out what is our distance. Okay, the trolley moves at a distance of 7 meters up, so it's also shown in the diagram. So our distance is therefore 7, change in distance. Cos, what's our theta? Okay, did they say anything about theta here? All right, trolley is at rest, constant horizontal force applied. Point A, remove, okay, which is a height of B at point B. The trolley experiences a constant frictional moving up the incline. Okay, so at this point then, we're just gonna use theta as 180. Okay, let's move on. Our m is still pretty much the same. Remember, it was 2. Let me put this in bracket. 2. G is still 9.8, and our final h, that is actually what we're looking for, minus, okay, m is 2, g, and our initial h is 0. Remember, initially we are down here, so there's no h there, it's 0. So I'm just gonna put 0 here, okay, to save space, plus our final velocity, okay, it's half, okay, mv, our final velocity Okay, remember this thing, it reaches a maximum height, meaning at B the velocity is 0. So it's coming up with a velocity there and it reaches a velocity of 0. That's gonna be our maximum height. So I'm gonna put 0 there, minus half. M is still gonna be 2, and then our initial velocity, we calculated it over here, is 4.9. Okay, so we've got 4.9 squared. Cool. All right, so all we have to do now is just some mathematical gymnastics. Oof, it's gonna be a lot of work, but let's get right into it. We'll use the calculator once. So this stays exactly as it is. Cos of 180, cos of 180, it's like minus 1. So I'm gonna put minus 1 here. And then 2 times 9.8 h. I don't know it by head, so I'm just gonna put 2 times 9.8 h. And then here I have minus, well, these halves, they cancel each other, so I'll have 4.9 squared. Now to get h on its own, I'm gonna have to say 1.5 times 7, and it's negative. Let me just put the negative because of that negative 1. And then I want to take the 4 squared to the other side, so I'm gonna have plus, okay, I'm gonna have plus 4.9 squared. That's gonna be equals to h. So I'm gonna divide both sides by 2 times 9.8. So I have 2 times 9.8. Okay, so potentially this is what I want to put in the calculator. So let's get our calculator. Okay, calculator, let's put it this side. Right, so what do we have? Let's put our fraction there. It's negative 1.5 times 7 plus 4.9 squared. We come down here, we put 2 times 9.8. Okay, and then what do we get? 0.689. Do I want it in 2 decimals or 3? Let's do it in 2. So it's gonna be 69. Thank you, calculator. Therefore h, therefore the height is equals to 0.69 meters. That's it. That's our final answer right there. Let's see, do we have anything else to answer? That was the final question. Well, ladies and gentlemen, I hope you understood, but in the event that you didn't, do contact me through my website www.mvtutors.co.za. book a free consultation there, or alternatively you can WhatsApp me on 076 3112-1107. And remember, involve your parent. Ask your parent before you contact me, because they are the ones who are going to be paying for your sessions with me. Okay, well, thank you so much.
Hello everyone and welcome to MV Tutors. I'm Tsulu and I'll be looking at question 6 with you from the physics prelim that you wrote recently. Alright, let us see what they are saying about it. Alright, so a group of grade 12 learners stand outside a fire station when a fire engine races past them on a call. The siren of the fire engine emits a sound with a frequency of 250 Hz while moving at a speed of 20 meters per second past the learners with flashing red lights. The group of learners notice that the sound of the siren changes as the fire engine moves away from them. Take the speed of sound of A as, or speed of sound in A as 340 meters per second. Okay, so yeah, you have a group of students and this, what is this? Fire engine. Yeah, the siren of the fire engine, it emits a sound and it moves past them. Okay, so obviously as it is next to them, they can pretty much hear the same frequency, but when it moves away from them, the wavelengths keep increasing. Okay, and wavelength is inversely proportional to frequency. So the bigger the wavelength, the lower your frequency. The smaller the wavelength, the higher your frequency. Okay. So now, 6,1, name the phenomenon described in the underlined sentence above. Okay, so it says the group of learners notice that the sound of the siren changes as the fire engine moves away from them. Okay, so that is the Doppler effect. That is the phenomenon here. Okay, now how would each of the following change as the fire engine moves away from the learners? Okay, the frequency observed by the learners. Okay, so initially, guys, you have the learners here all standing. Okay, and you have this this fire engine next to them. Okay, I don't know how I'm gonna show that, but yeah, something like that with the light there and the siren. Okay, and it's moving away, basically away from them. So as it is emitting sound or frequency, okay, so when it's near them, we have something of this manner. Okay, the waves are gonna be like, no, this is not working out. Okay, so the waves are actually closer to each other at the beginning, okay, than they are at the end. So it would look something, yes, this is what I wanted to show. Okay, so this is when it's near them. Okay, so the wavelength is actually shorter here. Okay, but once you have the truck moving or having moved away from them, yeah, no, this truck. Okay, now you have the waves actually just okay, now how do I do it? So they are, okay, so now the spacing of the wavelength is getting bigger and bigger as it moves away from them. But when it was near them, the spacing was actually smaller. Okay, so now let us see what are they asking us. So the frequency observed by the learners when the engine moves away. Okay, because when the engine moves away, the wavelength is actually higher. It means the frequency is actually less. So we would go for less than. Okay, then when we get to 6.2.2, the speed of the sound in the air. Okay, guys, you have air here, you have air there, air everywhere, which is the same. So yeah, that will actually stay the same. So stays the same. Yeah, please remember just to use the descriptions that they use. Okay, because they actually told you what you should be choosing from. Yeah. Now it says, calculate the apparent frequency of the sound from the siren observed by the learners when the fire engine moves away from the learners at a speed of 20 meters per second. Okay, let's have a look at the Doppler effect equation. Alrighty. Okay, so we have the frequency of the listener, which are the learners. Okay, then you have the speed of air. Then you have the speed of the listeners. Again, the speed of air. And the speed of the source, okay, which is the fire engine. Okay, you realize I haven't actually put the science yet. And then we have the frequency of the source. So how do you know which one is negative and which one is positive? Well, basically, if the listener is moving away, if the listener is moving away from the source, then it would be a negative. Okay, if the listener moves towards the source, then it is a positive. If the source moves away from the listener, it is a positive. And if the source moves towards the listener, then it is a negative. Okay, so now what do we have here? We actually have the source moving away. Okay, so in this case, we will have a positive here. In terms of the listener, well, the listener is stationary, so it doesn't matter whether you use a positive or a negative. It doesn't matter. So I'm just going to use positive. So yeah, positive or negative, it doesn't matter. Okay, now the velocity of the air, they've already given it to us. Okay, and that is 340 meters per second. And you know that the listeners are stationary. Then the velocity of the air again, 340 meters per second. And that of the source, I think they said 20. Yes, 20 meters per second. Okay, and all of that is multiplied by the frequency, which is 250. Okay, so we're just going to calculate quickly. We have 340 here, and we have 340 plus 20. I know you're like, obviously that's 360, but trust me, you can make errors. So just put everything as it is. So that, and then we multiply that by 250, which is 236,11. Hertz, because we're getting the frequency. Okay, so that is the apparent frequency of the sound from the siren observed by the learners. Now 6.4, what are they asking? So it says draw a diagram to show the advancing wave fronts that are produced by the sound as the fire engine moves away from the learners. So clearly indicate the learner's position and the direction of the fire engine's velocity in the diagram. Okay, guys. So it's pretty much what I drew here, but let's try and attempt it again. So you have the learners, right? I don't think you have to draw stick figures or anything like that. You can just put L there, okay, for listener. Okay, and then you have the fire truck that has moved away. Okay, even for this, I don't think you have to like put something hectic. Okay, I've had some practice. And you can see it's moving away. You indicate it, right? They said we should clearly indicate the learner's position and the direction of the fire engine's velocity. Okay, and then we should show the wave fronts advancing. So as it is moving away, okay, like I had drawn previously, now you actually have the sound waves being much bigger. Okay, yeah. I don't know, but maybe I should have just made it solid. But yeah, basically, as it moves away, the wavelengths become bigger. So the space in between the wavelengths, that actually becomes bigger. as it moves away. Okay, and as a result, the frequency then would decrease. Okay, like you saw, first it started off as 250 when it was close to when the learners were close to the fire engine as it was moving out, but the further it moved away, it became less, 236. So you must show actually that the wavelengths on this side are actually bigger compared to the wavelengths here. Okay, and I did indicate it there. When it moves away, it looks something like that. When it's close to them, it looks something like that on the left. But yeah, that is pretty much how you would sketch it. All right, last question, 6,5. So it says there is a noticeable change in the frequency of the sound, but no noticeable change in the color of the flashing red light as the fire engine races past the learners. Explain these observations, and this is 3 marks. You're like, where in the world do I begin? Okay, guys, so as you've seen with the siren, the light remains red. You can even see it from a distance. I mean, even with police cars, you can see that blue light from, I almost said a mile, but yeah, you can see it from a distance as well. So why is it that when it comes to sound, the frequency is obvious, but when it comes to light, it's not so obvious? Okay, so yeah, how I would tackle it is the frequency of the sound, or rather how do I put it? I would say the speed of sound, okay? So the speed of sound in A, okay, is way less than the speed of sound, or rather, let me just say the speed of light. Okay, so the speed of, speed of sound in A, they gave it to us. It's like what, 340 meters per second. And the speed of light, geez, I forgot it. I think it's that value C. Yep, it's like 3 times 10 to the power 8 meters per second. So you can't really compare the two. The speed of sound in A and the speed of light, you can't compare them. They're just incomparable. But you can compare the speed of sound in A and the speed of the moving engine, fire engine, yeah. Okay, its speed was what? The A, that's 340. And then for the engine, that was like what, 20. So there's comparable. Hence, you can talk about the differences between them. Okay, the speed of sound and the moving fire engine, and therefore you can talk about the frequency in that sense. But when it comes to the speed of sound in A and the speed of light, those two are incomparable. The speed of light is way too huge, too big. Okay, so therefore, even from a long distance, you can still see the red flashing lights. Okay, so yeah, I hope you can put it nicely. But basically, you're comparing the speed of sound in the air and the speed of light, and you can conclude they're incomparable. Speed of light is way too big, so you can see the color of the flashing lights from a distance. But when you look at the speed of sound in A as well as the speed of the moving vehicle, the fire engine, they're actually comparable. And because they're comparable, you can tell the frequencies apart. Okay, I don't know if they'll actually yeah, I think that's good enough. I hope. So yeah, I hope you understood. I hope you learned something with this section on the Doppler effect, and I hope you did well in your test. So please don't forget to like our videos and also subscribe to our channel. But yeah, it's goodbye from me until next time.
Well, good day to you, good day indeed. Welcome to MV Tutors. My name is Figa and I'll be your tutor today. So, we're doing the Gauteng prelims and we're on question number 7 now. Please like and subscribe this video so that more people can get to access it as well. And if you will need me to be your tutor, I'm available for you, but please before you contact me, speak to your parent or guardian, let them know and show them this video that we exist. And remember that your parent or guardian is the one paying the fees, so they are the ones that are going to have to pay me to tutor you, so involve them first. Okay, let's get right into it. Question number 7. A metal sphere X with a charge of 5 and it's positive is suspended by an inelastic thread of negligible mass which is tied to the ceiling at point M. Okay, I see it there. Another metal sphere Y there on an insulated stand has a charge of -8 and is brought closer to sphere X until their centers are 20 millimeters apart. Okay, I see what's going on here. Then state Coulomb's law in words. I wouldn't want to assume you know it, but you should be knowing it by now. Okay, but let's just get it out there. Okay, so if you want Coulomb's law in words, first let's just go get a clue, and there it is there. If you look at this, that's gonna give you the clue. This is Coulomb's law over here. So let's write it down. Let's go back. This is from your formula sheet. Oof, excuse me, it's just burping. We're just gonna write that it was F is equals to Q1 Q2 divided by R squared. So then in defining in Coulomb's law in words, you're gonna say the magnitude of the electrostatic force so this is the force we're talking about here. Okay, exerted by 1 point charge let's call it Q1. Okay, on another point charge, I'm gonna call it Q2. Okay, is directly proportional okay, is directly proportional to the product. Remember, we're still talking about the force. It's directly proportional to the product of these charges, to the product of the charges and let me just give us more space, and inversely proportional to the square of the distances between them, of the distance between them. That's that R there that we're talking about. Two. That's it. So all we did was just put this formula in words. The force is directly proportional to the product of the charges and inversely proportional to the distance between them. Okay, let us now go and see what the next question is actually saying. 7.2 says calculate the magnitude of the electrostatic force that sphere 1 exerts on sphere X. Okay, so we're just gonna apply this formula. That's basically what they're asking us to do right here. So let's do that real quick. All right, let's use a red pen this time. We are doing 7.2. So we know that the force is equals to Q1 times Q2 divided by R. Now we need the numbers. What is Q1? Okay. Okay. So wait a minute. There is a K there. Okay. So let's put the K. That's the constant. Okay. So having put the constant, we know that the value of that constant, you can check it in your formula sheet. It's always there. So you don't need to memorize it, but it's 9 times 10 to the power 9. And then let us put the Q1. Q1 is actually 5, but it's in nanocoulombs. So to convert nano is 10 to the power minus 9 to coulombs. And then times the other one is 8, and it's also nanocoulombs, so we 10 to the power minus 9, convert it like that, and all of this is going to be divided by the distance between them. Now the distance is actually 20 millimeters. In millimeters, we'll need to convert them to meters, so that's going to be 10 to the power minus 2, but it has to be squared, so the distance has to be squared like that. Okay, now we just have to put this in a calculator and see what it gives us. Let me get a calculator real quick right over there. So my calculator, I'll put it there. So I'm gonna put that, and I'm gonna say 9. Okay, so we've got times 10 right here, times 10 to the power 9. Okay, but okay, I don't want to do it this way because it can get confusing for a lot of people. So I'm just gonna put it raw. So it's 10 to the power 9. Okay, and then come downstairs, and then we're gonna say times 5 times 10 to the power, let's put it, minus 9. We'll come down again, and then we say times 8 times 10 to the power, let's put the power thing again, minus 9. Cool. Then let's go downstairs. Downstairs, let's open the bracket, put it exactly as it is, 10 to the power, okay, we've got minus 2. Come downstairs, we close the bracket, and then we put exponent and we put the 2. So we put everything exactly as it is. Okay, and then our final answer is 9 times 10 to the power minus 4. Thank you very much, calculator. So the final answer was 9 times 10 to the power minus 4 newtons. That is our force. Okay, now let's go to 7.3. 7.3, draw the resultant electrostatic field pattern produced by sphere X and Y. Well, you should know by now that from the positive, if you have a positive charge, let me just put the negative. Electrons are actually are moving out here. Okay, they're moving out. Okay, so I'm just gonna put them like that. So they're moving out, they flow out from positive to negative, like that. So moving out, moving out, moving out. But here on the negative, we actually know that they are moving in, moving in, moving in, moving in, and moving in, moving in, moving in. That's it. This is 7.3. Okay, that's all. And then 7.5 sphere, Y is now moved closer and makes contact with sphere X, after which sphere X is repelled. Calculate the new charge on the sphere. So once they make contact, they start sharing their charges, and those charges are actually evened out. So what we're gonna do then, 7.4, is that we're gonna average them. So it's gonna be that charge, it's gonna be that charge on X, okay, plus that charge on Y, and we even them out. So we divide by 2. That's gonna give us our new Q. Okay, so this one was 5, and then this one was minus 8. Okay, and I want to convert them, so I'm gonna say times 10 to the power minus 9 divided by 2. Okay, so now you have to include the minus sign because it's the direction. Okay, let's give us more space. I think let me bring out the calculator at this point. But what's 5 minus 8? 5 minus 8 is minus 3. So we have minus 3 times 10 to the power minus 9 divided by 2. Okay, I don't need a calculator for this because minus 3 times, divide by 2 is minus 1.5 times 10 to the power minus 9 coulombs each. That's it. Let's put each. That's our new charge. That's it. Well, in the event that you didn't understand anything, do contact me via my website, which is www.mvtutors.co.za, or contact me via my WhatsApp, which is 076-312-1107. And remember, before you contact me, speak to your parent or guardian about tutoring. I would love to be your tutor. Okay, thank you.
Hello everyone and welcome to MV Tutors. I'm Tsulu and I'll be looking at question 8 with you guys from the prelim you recently wrote. Alright, so a battery with an EMF of 8 volts and an internal resistance R. So you see here, internal resistance R, and here you have 8 volts from the battery, is connected in a circuit as shown below. Okay, if switch S1, there is S1, is closed, the reading on the voltmeter is 6,86 volts, and on the ammeter is 2 amperes. Okay, so basically what they're saying, when the switch S1 is closed, you have the cell providing the maximum voltage. Okay, and in that case, no current is flowing. But as soon as there's current flowing, you then have a reduced voltage, which we call our terminal potential difference. Okay, so it's velocity, it's VTPD, terminal potential difference. All right, so this 6,86, that is your VTPD. Okay, and yeah, because there are some lost volts due to this current that has now is now flowing through the circuit because the switch is closed. Okay, so that is what happens there. And now 8.1, they're saying explain the meaning of an EMF of 8 volts. So if I were to loosely explain this, I would say the maximum voltage that the battery can provide to the circuit is 8 volts, provided that no current passes through or there's no current flowing. Okay, but that is a loose term, okay, or rather meaning of EMF. The one that's more correct is to say that so the maximum work done by the battery, the maximum work done by the battery per unit charge is 8 volts. Okay, so I think that will land you 2 marks. But as for what I had said before, I don't know about the full 2 marks. Maybe you can ask your teacher if that would count. All right, and then they say calculate the internal resistance R of the battery. Okay, so you know your equation, if we go to the formula sheet, for EMF. Okay, so I'm just going to say EMF actually. EMF is equal to your current that is flowing through, where we know that is 2. Okay, another way of writing it, okay, if you expand that out, okay, so that would be the volt, okay, of the terminal potential difference. Another word for it, instead of saying terminal potential difference, is basically the reduced volt. Okay, so I'm just going to write in brackets there. It's actually the reduced voltage. Okay, whereas here we have V lost. So that is actually the volts or the voltage that was lost as a result of the current flowing. Okay, so basically then the reduced volts, if we go back to our question, okay, the reduced volts actually is 6,86. Okay, and we don't know what the lost volts are because we're trying to get the internal resistance. Okay, so the lost volts, I'll just put it as IR. And the EMF they gave it to us is 8. So IR, you know that, okay, let me just say 8 minus 6,86 is equal to 2 times R, because they gave us the current flowing, which is 2 amperes. Okay, so you have 8 minus 6,86, it's 1,14. Okay, so 1,14 divided by 2 will give us our internal resistance. 0,57. And the unit there is ohm. Okay, and yeah, that is the internal resistance of the battery. So now 8.3, calculate the value of the unknown resistor R1. Okay, let's have a look at the circuit again. Okay, so what are we going to do? What is our strategy? What I propose is that we actually take these two parallel resistors and make them one. Okay, so we're going to turn all of these into one resistor, and we're going to add those resistors that are the total resistance, right? So we have this one that we have resolved from parallel to now it'll be in series. Okay, and then we have to figure out what the total resistance is. Okay, so let's start with the parallel one. So 1 over the parallel resistance, you have 1 over R1 plus 1 over 2. And what we do there, we want to get a common denominator. So you multiply these two and then you cross multiply. Okay, so you're going to have 2R1 at the denominator, and then 2 times 1, that's 2. 1 times R1, that is R1. Okay, that is still 1 over the resistors in parallel. So for you to get the resistors in parallel, we're just going to flip it. Okay, so you have 2R1 over 2 plus R1. So that is our resistance over there. Okay, then we should have our total resistance, which is going to be the resistors in parallel, as well as the 2 over there. But how do you get your total resistors? Remember, while the current was flowing, you had the reading on the voltmeter as 6,86. So if you want to get the total resistance, you, bearing in mind that velocity is I times R, so R is V over I. Okay, this is just you knowing that for yourself. So the total resistance then would be the volt, the terminal potential difference, over the current, which is 2. Okay, and you have your parallel resistors there, and you are adding it to the one in series. Okay, so your terminal potential difference is going to be 6,86 over 2, and then you have 2R1 over 2 plus R1 plus 2. Okay, so 2R1 over 2 plus R1, it's going to be 6,86 over 2 minus 2. Okay, and then we're going to take 2 plus R1 and we're going to multiply by whatever value that is. Okay, so we have 6,86 all over 2 minus 2, and that gives us 1,43. Okay, so 2 times 1,43 is 2,86. And I have 1,43R1. Okay, so now 2 minus 1,43 is 0,57. What are we calculating for? The unknown resistor, R1, yes. It's always good to just check what exactly it is you are doing before you get too far. Alright, so now 2,86 divided by 0,57, we get 5,02. So there we have it, 5,02 ohm. And that is the value of the unknown resistor. 5 marks. Okay, I think this was worth 5 marks. Okay, and now we get to the term power. So guys, if you don't remember your definitions, sometimes your formulas actually help. Let's go see if we can find power there in the formula sheet. Okay, so there are there are 4 formulas pertaining to power. If you can write any of these in words, that's great. I'm gonna go with the first one. So power is actually the rate at which work is done. Okay, because it's W over delta T. If you see delta T, you know rate. Okay, so work, the rate at which work is done, that is power. And there you have it. Do you have what? Was it 1 mark or 2 marks? 2 marks. So yeah, no need to go far. Now they're saying switch S2 is now opened. Where is switch S2? And how will that have an effect? What effect will the power dissipated by R1 have? Okay, so R1, when the switch was closed, okay, now it's opened. So what will happen if this is opened? Where will the current go? Or where won't it go? Okay, so you have your current. Remember, current flows from the positive terminal to the negative. So you have a current going this side. S1 is closed, okay? And then the current, remember here it is open now. S2 is open. Now the current is going to go this side, okay? All of it. Remember, we calculated that R1 is 5,02 ohms. And if you have the whole I, which is equal to 2 amperes flowing through it, then your voltage is now going to be 5,02 times 2, which is going to be 10,04 volts. Okay, previously you would have had a portion of the current going this way and a portion going that way, so it wouldn't have been 10, it would have been less. Okay, so you have that current flowing, and then it flows all the way and it goes until it reaches the battery. Okay, so that's basically what's happening. But now they want us to know, or they want us to state what will happen to the power. Okay, what effect will the power dissipated by R1 have? Okay, so again, battery dying. Okay, so looking at the power equation, let's just look at it now. The other ones, I'm just going to take P is equal to VI. Sorry, I just went away quickly. Okay, so if I have my power equation, it's equal to V over I. Okay, there's another one where it says it's equal to V squared. Okay, so if you change the I, you would have V over R, so it would be V squared over R. And if you change the V, you would have I squared times R. But let's just focus on this. Okay, basically power is directly proportional to the voltage. I almost said velocity. Power is directly proportional to the voltage. If the voltage increases, the power increases. And we can see it in the formulas. If you increase V over here, your power will also increase. If you increase V over here, the power will increase. So with all of the current going to resistor 1, your voltage has increased at resistor 1, and power will obviously also increase. So let's see, what effect will the power dissipated by R1 have? It will increase. Explain your answer. Well, basically, power is directly proportional to voltage. Power directly proportional to voltage. Okay, and why would that be? You would have to explain that you're getting the full current going through resistor 1, and therefore your voltage has increased as a result. And because the voltage has increased, it means the power will also increase. And you can leave it there and be done with question 8, like we are right now. So yeah, I hope you have learned something. Again, please share with your fellow matric friends. Yeah, and also if you require tutoring, please, you can show these videos to your parents to show that, you know what, mom, you know what, dad, these people are reputable, they know what they're saying and doing. And you can schedule a lesson. You can visit our website on www.mvtutors.co.za. And also please like our videos and subscribe to our channel, and advise your friends to do that as well. Thank you. Hello everyone, and welcome to MV Tutors. I'm Solo, and I'll be looking at question 9 with you guys. We are almost there, so let's just stick it through until my husband comes in with question 10. Okay, so let us get right to it. And thank you for tuning in, by the way. Please don't forget to like our videos and subscribe to our channel. Also tell a friend, fellow matric learner, your parents. Spread the news, guys. Alright, so the diagram below shows a simple generator. Remember, a generator, that's where you take mechanical energy and produce electrical energy. We should know that in South Africa, since there's a lot of load shedding going on. Alright, so we have part A here, which would be like your coil or your loop. And then we have part B. The fact that it is, let me just, the fact that it is split over there, you would call it a split ring commutator. Okay, it is split. All right, so let me just delete that. Just wanted to indicate how you actually see. Alrighty, and now 9.1, they ask, is this an AC or a DC generator? What do you think? Well, if it were an AC generator, you would have slip rings, okay? Slip rings. Let me just write that. So for an AC, okay, you have slip rings. Okay, but for a DC, you have a split ring commutator. Okay, so in this case, we have it split. Okay, you don't have two rings that you slip in. No, you have a split ring. Okay, so it is a DC generator. All right, and then give a reason for your answer. Well, because we have a split ring commutator. Okay, whereas an AC generator consists of slip rings. I think that is worth 2 marks. All right, so write the name of part A. So part A here, this would be like a loop. I would call it a loop, or maybe another term for it would be a coil. Okay, but I think loop sticks in the mind more than a coil. Whatever floats your boat, rather whatever rocks your boat. I don't know which one is which, but yeah. Okay, now they say describe the energy conversion that takes place in a generator. Like I said, in South Africa, we know this best, especially those who can afford when the electricity goes out, load shedding, or what do they call it these days? Load reduction. You know, you can use a generator. Okay, so it takes mechanical energy and transfer it to electrical energy. And boy, are these generators loud. I think they should work on a design where they somehow kill the sound. Okay, engineers, where you at? Come on. All right. Now they're saying the maximum EMF generated the maximum EMF generated is 15 volts. Okay. Draw a sketch graph of EMF versus time for 1.5 cycles of this generator. Okay, so you know that the graphs for a DC generator is quite different from the ones of an AC generator. Okay, so we have the vertical axis there, horizontal axis. Okay, so on the vertical, you have EMF. Okay, because they did say it's an EMF measured in volts versus time. Time is normally in seconds. Okay, so for a DC generator, 1.5 cycles. So this is half the cycle. Okay, another half, and another half. So 1.5. Okay, if you had an AC generator, it's like a complete wave. So you would have your first half and then the full wave. Okay, and then you'd have 1.5 like that. So that is the difference between the two. Okay, but we are dealing with a DC, not an AC. Okay, so, and we need to indicate, they said the maximum EMF generated is 15 volts. So this is the maximum you will reach. Okay, so that would be 15. Okay, if you had the AC one, we would do something like that and like that. You would have to indicate there as 15 too. But like I said, we are dealing with a DC. So that's what we have. Alrighty, and now we get to 9.6. Okay, so 9.6, the specifications of a professional hair dryer are as follows. So your power rating is 2100 watt, and the AC motor is 240 volts. Okay, so I'm just gonna write those down. Whenever you see this power that they give you, it's actually the average power. Okay, so just make a note for yourself that is actually the average power, and the voltage that they give you, it's actually the RMS voltage. Okay, so that is 240 volts. Just note that for yourself. All right, so now they go on to say, define RMS for an alternating voltage. Okay, so the RMS, which is basically the root mean square for alternating voltage. Okay, the root mean squared for the alternating voltage is the direct current potential difference, which dissipates or releases. Let's just stick to dissipate. Yeah, which dissipates the same amount of energy as the alternating current. Okay, so yeah, that is the RMS for an alternating voltage. It's basically the DC potential difference, which dissipates the same amount of energy as the alternating current. Okay, now 9.6.2. And how many marks is that? Definitions are normally 2 marks. So what is the RMS voltage for this dryer? Well, basically, remember they told us that the AC moto is 240, and we did say that this root mean squared, or RMS, for the alternating voltage is actually the DC potential difference, which dissipates the same amount of energy as the alternating current. So if they gave us the alternating current, well, it would actually be the same as the VRMS, which is 240 volts, based on the definition we gave. Okay, and then the last question of 9.6. Now they're saying, calculate the maximum current that might flow through the hair dryer. Okay, maximum current. Let's have a look at the equations that they give you and how you can make use of them. Okay, so we have that the average power, okay, or AVE, not AVG, is actually equal to your RMS voltage times your RMS current, okay? And we also have that the root mean squared current is equal to the maximum current over root 2. Okay, so going back to our question, they want the maximum current. They want this. Okay, so we're going to start here. We have our average power. It was given to us, 2,100 watts. And we also have our root mean squared voltage, which was equal to 240. So now we can get our root mean squared current. Okay, it's actually 2,100 over 240. Okay, it's 8,75 amperes. Okay, now we need to get the maximum. All right, so we have that equation there. I'm actually going to write it in terms of the maximum. It's actually the RMS current times root 2. Okay, so I max is root 2 times 8,75. Or maybe let me just put it there where I started and not complicate things. Okay, and if we work that out, finally we have root 2 multiplied by 8,75, and that is going to be 12,37 amperes, and that would be the maximum current. Okay, AC current. So basically, if you were to have your graph okay, and you were looking at the maximum current there, that would actually be 12,37, but the root mean stands somewhere here, okay, which should be 8,75. okay, that's where that were to be current and time. Okay, yeah, so I hope that made sense, and I hope you guys understood. This is not what they were asking, but basically, yeah, that's how it would look. And yeah, guys, so this is the end of question 9. Like I said, my husband is next with question 10, so enjoy. Please do not forget to like our videos and subscribe to our channel where learning takes place. Okay, both maths and physics, we got you guys. All right, bye.
Welcome to MV Tutors. My name is Figa and I am your tutor. Please, first of all, please like and subscribe this video. This will help other learners to reach us so that they can view these very same videos. But other than that, if you would like me as your tutor after this, please do contact me. But before you do contact me, show this channel to your parents as well, or guardians, because remember, they are the ones paying the fees after all. And if you want me as a tutor, they will have to pay. So involve them before you contact me. All right, but let's get right into it. We are doing the Gauteng prelims, and we are now in question number 10. This is the last question. Let's get right into it. It says the apparatus shown below allows for several variables in the investigation of photoelectric effect. A learner sets up the apparatus and measures the maximum kinetic energy of photoelectrons emitted from the surface of metal X using different frequencies of the incident radiation. Okay, so that's the incident radiation there coming at an angle, and that's the metal there, and then these are the apparatus connected to that. Okay, I see what's going on. First of all, they say 10.1, describe the term photoelectric effect. Okay, let's do that. Let's get a pen. Let's describe it. You should know it by now, but I don't want to assume that you do, so I'm just gonna write it down for you. Okay, so this is the process. Okay, the process whereby, now if you look here, this is the processes whereby the electrons, okay, from a metal surface, when lit with this incident line, let's just write it down. Let's write it down before I explain it practically. The process whereby electrons, okay, are ejected from a metal surface when light of suitable, okay, where light of suitable frequency is incident on that surface. Okay, the process whereby electrons on the surface are ejected from a metal surface when light of suitable frequency is incident on the surface. So as you shine the light here and it reaches a certain frequency, certain electrons are going to be ejected from this surface, and then they'll move whatever. Yeah, they will move where, I guess in this apparatus they will move into this wire there. Okay, so let's see the next question. So now they say light of different wavelengths is shown onto metal X and the kinetic energy is measured. Name the independent, dependent, and controlled variables. Okay, so you should know these based on theory as well. 10.2.1. So let's start with the independent one. Dependent. Okay, so the independent one would be the frequency right there. It's independent. It's not dependent on anything. And then the dependent one dependent. The dependent one therefore will be the kinetic energy of the electrons, or let me just say the electrons. Where is it? There. The electron kinetic energy. I need more space. Let's give each other more space. Why are we struggling when we have so much space? What was I saying? Electron kinetic energy. And then the last one was, what is it? The controlled variable, the one that is the controlled variable, meaning the thing that you vary, that changes, that will be the type of metal. You change the type of metal. The controlled variable, the variable that is consistent here is the metal. Okay, it's control. Now let's go to 10.2.2 now. When ultraviolet light with a wavelength of 200, okay, is shown onto metal X, the kinetic energy released electron is that joules. Identify metal X in the table given above. So what do we have to? We have to calculate the work function, and then once we calculate the work function, it will give us a certain number, and then we'll just come back to this table and see which number does it correspond with. Whatever number it corresponds with, that will be the metal that we are looking at. Okay, so now the first thing that we need to get is the correct formula. Let me just do this. I'll put it right here. This is 10.2.2. all right, let's go to the formula sheets. Now when you go to your formula sheet, there we go. The formula that's work function over there. So the formula that we will go with is this formula. Okay, so let's just write down that formula first, and then we'll take it from there. So that formula was E is equals to work function, okay, plus the kinetic energy. All right, now let's go further, define it. For work function, we will take, for the energy there, we'll take this formula, okay, because we need to work it out. So E was H and then C over lambda, the wavelength. That's equals to work function, that's what we are looking for, plus the kinetic energy, which we are given. Okay, now we can start filling these in. H is a constant, and it is 6.63 times 10 to the power negative 34. It's there in your formula sheet. Okay, and then we have to multiply this with C. C is also a constant, and it is 3 times 10 to the power 8. It's there in your formula sheet, and I'll just put one division sign. Lambda we are given is 280, so we're just gonna say 280, but we need to convert it since it's nano, so it's 10 to the power minus 9. Okay, so this is gonna be equals to work function. All right, let me just rewrite that. Work function plus where am I gonna write it now? It's gonna look untitled. I don't know why I'm straining myself with space, but anyway, we've been given this 5.7. That's the kinetic energy we're given right there, and it's 5.774 times 10 to the power minus 20. Cool. All right, so I just want to put this in a calculator. Make this the subject of the formula, so I'll put this and then I'll subtract that. Okay, let's get a calculator. Let's bring it this side since we've got space. So I will put that, and I got 6.63 times 10 to the power negative 34. I'll come down and then say times 3 times 10 to the power 8, and then we'll come down and then we'll put 280 times 10 to the power. Why didn't anyone tell me that it's not negative 9 there? It should be negative 20, because that's what we're given in joules. Okay, so we're gonna put negative 20 there. Okay, what's that equals? Oh, look at that. And then we're going to subtract this, because we make here work function the subject of the formula. And if I take this to the other side, it changes sign from being plus to a minus. So I'm gonna say minus 5.7. Oh, no. See, I made a mistake. Sorry, guys. Now, I just remembered this is to the power negative 9. I was thinking of this. Now, naturally, I would cancel this. and re-record, but I don't like doing that, because I want you to know that when you make a mistake, you must re-evaluate and try again. Okay, it's very important. So this is what you do when you make a mistake. You re-evaluate your mistake and say, I put negative 20 there instead of a negative 9. So that's my re-evaluation, and then here is me trying again, and this time I'm going to put the right thing. So there I'm gonna put 280 times 10 to the power negative 9. Okay, I think we're cool now. That's our answer. Minus 5.74 times 10 to the power. There's our negative 20. It goes there. Good. So I get 6.5. 2 decimals is 5.3 times 10 to the power 19. Thank you. So that was 6.53 times 10 to the power negative 19 joules. That's our work function. All right, let's now go to the last question, which says that the maximum kinetic energy of the electrons ejected. Oh, wait 1 minute. I just remembered that we are supposed to identify metal X, okay, in the table above. So if our work function is 6.53, we need to come back here and say which one of this is 6.53. 6.53, no, there it is. So our metal is aluminum, which is gonna say, therefore, metal X is aluminium. Aluminium. Okay, so that's our final answer. Cool. Now we can go to the next question. The maximum kinetic energy of the electrons ejected from this ultraviolet light is greater than the maximum kinetic energy of the electrons ejected by the bright blue light. Explain why this is so. All right. This is theory work, so but let's just write it down. Okay, so number one, you need to understand that the photon energy, increases, okay, as the frequency okay, as the frequency of the light increases. Okay, number one, you need to understand that. Then the intensity only increases the number. Okay, let's give ourselves more space. Okay, increases the number of electrons not their average kinetic energy. Okay, so in intensity only increases number of electrons, not the kinetic energy. Therefore, the ultraviolet light will, let's give ourselves more space, ultraviolet light will release electrons with a higher kinetic energy. That's it. Okay, so photon energy increases as the frequency of the light increases, but the intensity only increases the number of electrons, not their average kinetic energy. Intensity has nothing to do with kinetic energy. Therefore, the ultraviolet light will release electrons with higher kinetic energy. All right, that's it. Well, I hope you understood all of that, but in the event that you didn't, do contact me. I would love to be your tutor via my website www.mvtutors.co.za, or alternatively you can WhatsApp me on 076 312 1107. And remember, before you contact me, speak to your guardian or your parent before you contact me. Show them this video. It will make them trust us and build credibility with us as well. And because they are the ones who are paying for the session, so they have to be involved. Other than that, it's goodbye from me.